Hi everyone, so we've looked at substitution reactions and how to determine if something's going to go SN1 and SN2. Now we can look at elimination mechanisms. So these are the other mechanisms that compete with SN1 and SN2, and they lead to different products. So in a substitution mechanism, we're substituting some group, let's say X, with some other group Y. It's in line with what the word substitution means. When we look at elimination, we're actually starting out with some group X, and then it's just eliminating. And we're getting an alkene out of it. So it's a fundamentally different reaction, but it competes for, it's a competing mechanisms for substitution. So substitution and elimination compete with one another, and then within those, within substitution and within elimination, you have different competing mechanisms. So it gets a little messy. Okay, so we're going to start with E2 here. So E2, the E stands for elimination, and the 2, just like in SN2, stands for second order, meaning that 2 molecules are involved in the rate determining step. So in an E2 mechanism, a strong base, we're just going to use the generic base here, B minus, I'm going to come in, grab a proton, and now that proton is going to fold down and kick out the leaving group. The leaving group still leaves, but you don't get substitution. You actually get an alkene. So this is actually the mechanism that we've already kind of looked at when we were making alkenes from alkyl halides. We went over that during the radical chapter, even though it wasn't really a radical mechanism. Yeah, so this is a nice way to make alkenes. For looking at how the rate of E2 changes, I don't know if it's the rate, but the competitiveness of the E2. This favors E2. So as we go from primary to secondary to tertiary, we're going to favor E2 as a reaction mechanism. So we already went over the regioselectivity for these reactions. Remember that if we have something like this, we really have two different protons in the beta position that can be pulled off to create the alkene. So if we pull off the blue proton, we'll end up making this alkene. And if we pull off the green proton, we will end up making this alkene. And so if we want to favor the one that's on the inside, the more substituted alkene, we use a smaller base. We can use something like OH minus, and if we want to favor something that is on the a less substituted alkene, so one of the protons that are at the periphery, we want to use a big bulky base. And we have names for these. They call this the Zaitsev product. If you're looking on the textbook or something, we call this the Hoffman product. I call it the less substituted and more substituted alkene. So I feel like those are easy to remember. Yeah, so big bulky bases tend to favor the Zaitsev product, the less substituted alkene, and smaller bases tend to favor the more substituted alkene. And you'll see here that you can use a strong base like tert butoxide or hydroxide, but also even stronger bases will work. You could use NH2 minus to try and get the Hoffman product, or you could use LDA, which remember is this kind of bulky base that looks like that. If you want to get the if you want to get the Hoffman product, you use you use this for the Zaitsev product, and you use this for the Hoffman product. The Hoffman product is this is the easier to access product in general. It's harder to gear things towards the Zaitsev product. So the stereoselectivity of E2 reactions is kind of interesting. So that's the radioselectivity, the Zaitsev-Hoffman thing. Stereoselectivity is kind of interesting. To get the reaction to go, the beta hydrogen has to be anti to the leaving group. And so when I say anti, I mean it in the sense that we learned about when we learned about conformational analysis. And we use the term periplanar, which means that they're almost in the same plane. They're not quite in the same plane. As far as we're concerned, they're in the same plane. But yeah, these things have to be anti-periplanar. And that means that the dihedral angle is approximately 180 degrees. So if we were to look at a Newman projection of this, let's say we're looking at it from the left-hand side. So let's say we're looking this direction. You can see our dihedral angle there. The way I've drawn it is exactly 180 degrees. It's actually a little bit off. That's what peri means in planar. It means it's not exactly in the same plane. We're not super worried about that. But yeah, because it has to be in this arrangement, it fixes the stereochemistry that you can have in the product. So we do the reaction on this. Let's say I take and I react this with hydroxide. We know that these have to be in the same plane, so the configuration at each of the carbons dictates what diastereomer you're going to end up getting. That hydroxide will come in, it'll cascade down. And we get this alkene. So in this alkene, you'll note the methyl groups are on the same side. Now if we started with a different stereoisomer, well, actually let's look at this one a little bit more closely. So let's say that you were given this problem, but the way it was drawn, the halogen was not antiperiplanar. What if instead it looked like this? Just some other conformation. You would not want to, for example, say, okay, well that must come down, and then this must pop off, okay? Because that'll give you the wrong stereoisomer, or may give you the wrong stereoisomer. I'd have to look at this one. Now what you should do is, if you want to be sure you get the right stereoisomer, is you want to rotate it to where it is antiperiplanar. So spin the bond here until you do get things in the same plane. So we can rotate around. We can hold this part of the bond stationary, and then we can rotate the other side back down. So actually in the opposite direction of my arrow. Oh no. Yeah, so we want to rotate that way. Is that right? Do I have that backwards? Yeah, sorry, the opposite direction. You want to rotate this way. Okay. And then if you rotate that way, you can put the bromine in the down position, leaving this stationary. And so everything gets transposed 120 degrees. So I rotated the Br group here. I rotated that down 120 degrees, which means that everything moves 120 degrees. Now I've got everything in the right position. Okay, so now you see it looks like the place that I started up here. And then you want to do your reaction. Then you want to take a look at this. So just be sure that when you're doing these problems, if you're going through an E2 reaction, that you have things in the antiperiplanar configuration that dictates what the stereochemistry is going to be. And you can kind of see, if you just look back at this other one, right? The CH3 and the CH3, they're on the same side here. And then, actually, let me be consistent with the colors here. They're on the same side here. And you'll see that they end up on the same side of the alkene here. Right? So, and that's not a coincidence, that's what's being fixed. That's what I mean when I say it's being fixed in the reaction mechanism. These are on the same side, they're both on the back bond, projected back out of the page, and they end up on the same side of the alkene. Right? So the configuration that or the conformation rather, that the substrate has to be in sort of dictates what the stereochemistry is. So if I were to take, let's say, and leave one of these chiral centers the same, and then swap the other chiral center. So now I'm going to take the hydrogen, I'm going to put it on the front, and put the CH3 group in the back. Okay? So everything is the same. If you're following, see this hydrogen, was this hydrogen up here at the top, and then this methyl group is in the back, and here we have the methyl group and the ethyl group are in the front still. So all I've done is I've switched the chiral center here. Okay, what happens now that I've switched one of the chiral centers? Well, now what we'll see is if I do this same reaction, what do I end up with? Now my hydrogen is on a different side. My CH3s are trans to one another. So we make the trans alkene there. So these reactions are stereospecific. And that just means that the stereochemistry of the product depends on the stereochemistry of the starting material. So we've seen this before when we looked at SN2, because the stereochemistry of the starting material dictates what the stereochemistry the resulting product is there as well. It's just inverted. So yeah, so whether you get the cis or the trans alkene, so at the top here, you know, or whatever you want to call it, E and Z, but whether you get the methyl groups on the same side or on opposite sides, so the E or Z or whatever you want to call it, is dependent on what the chirality or the stereochemistry is of the starting material. And so you have to be careful. The main thing that you have to be careful of when you're working on these reactions is just that everything, your stereochemistry is going to follow from putting this in the anti-periplanar conformation. So if you get everything in the anti-periplanar conformation, you should be able to hopefully see sort of where the stereochemistry comes from. But even if you can't, just everything that's on a wedge is going to be on the same side, and everything that's on a dash is going to be on the other side. Let's see, what else can we say about E2? I guess the other thing that you can get that's kind of weird is if you have E2 in a cyclohexane ring. Cyclohexanes, if we're looking at the chair configuration, for example, you can't rotate, sometimes you can't rotate into put a phenyl group down here, just something not reactive. Yeah, let's look at this. So CH3, I have a proton there. If I put this through, so yeah, let's look at this. If I put a base with this, those are anti-periplanar. So it's not a big deal. I can get that to work, no problem. Just like we just saw, that kicks off. And then I end up getting cyclohexene, and it would have this phenyl group that I added. But let's look at another scenario where we're looking at a different stereoisomer here. If instead the iodide is up here, hydrogen is here, and let's say the CH3 group is now axial. And again, we have this phenyl group back here. That's the phenyl group I'm just putting there so that we remove the potential for the other beta proton to be involved in the reaction. But now what do we see? Okay, these things are not anti to one another anymore, right? And so inside of the, when they're not in the ring and they're just kind of on a carbon-carbon bond, we can just rotate around to get the hydrogen in the right position. But here all we can do is go through the chair flip, which we can try, but it's not going to help us. Because it'll fix one thing, but mess up the other. Really, I should put another phenyl ring out here. Okay, so right, those are still not anti to one another. In order for them to be anti, there would have to be, the leaving group would have to be in the axial position and the hydrogen would have to be in there. So this molecule can't go through E2, even though it has a leaving group, and even if you add a strong base to it, it's unlikely that you can get it to go through E2, or if it did go through E2, it would go very slowly. Right? So that's just something to pay attention to. So sometimes you can't get it into the conformation you need to in order for it to react. And that means you just can't do that reaction. So our other elimination mechanism that we look at is E1. So E1 depends on just a single molecule's concentration. That's why it's 1, it's first order. So if we look at something like this, got a proton coming off of here. In the E1 mechanism, the first step, just like in SN1, is that leaving group pops off. And so I've got my carbocation, and now in the second part, my base, whatever base I'm using, will come in, take that proton, and form an alkene. And so yeah, so the E1 mechanism is strictly dependent rate-wise on the concentration of the substrate. As soon as the carbocation forms, it'll go on and form the alkene. So in terms of radioselectivity, this one always forms the more substituted alkene. So in E2, you can kind of gear it towards forming the less substituted one, the Hoffman product or whatever we called it. This one always forms the more substituted alkene. So if you're in a scenario like this and you're subjecting it to E1 conditions with a base, so I'll just go ahead and tell you, typically the base is something really bad like water. What you end up seeing out of this is this product. You will not see this. This is not observed. So you always get the more substituted alkene. And then for stereoselectivity, there's no conformational requisite here for activity like there was for E2 elimination. You just have a carbocation. So if you're looking at something like this, where you have two phenyl groups, and I subject this again to SN1 E1 conditions. Excuse me, I keep saying SN1 E1 conditions. What do I typically see? Usually, I just see the trans product, and that's just a thermodynamic thing. You probably see some of the cis as well, but the trans is generally preferred. Maybe you see some cis as well. So you'd say like major. And then this would be the minor product. And that's just, trans alkenes are just more thermodynamically stable. And it's for the reason that you think. It's just because they're farther apart. You know, if you look at this, for example, you know, when you have a cis alkene, it's kind of like those two groups are fixed in an eclipse position. And when they're trans, it's sort of like they're fixed in the anti-position, to draw an analogy to alkanes. And so that's pretty much it for E2 and E1 in terms of just looking at their mechanisms. E1, just like, I guess what I would say is E1 just like SN1. I would say, actually what I could say for E1 is everything that favors SN1 also favors E1. Okay, so you want something that can form a stable carbocation, you want a bad nucleophile, etc. All those things favor E1. Let's see. Yeah, in our next video, I'll go through one last thing, which is just look at carbocation rearrangements, and then we'll put this stuff all together and we'll look at E2, E1, SN2, and SN1 and try and figure out how we can predict which mechanism is going to happen and what are the products going to look like. Okay? All right.